Okay, on to the next section of our 3A1 Chapter 5. Just note we've moved on to Objective 3, so we skipped Objective 2. We'll come back to it in a little bit. So Objective 3 is define potential and kinetic energy. Calculate the energies of stationary and moving objects. Okay, so two different types of energy we look at. Potential energy is the first one. So potential energy is energy that is due to position, or essentially stored energy inside of an object. So if we've got some object and he's sitting up in the air, he has some energy that could be released if we drop him down. So how do we calculate potential energy? Well, we look at it as how much energy did it take for the object to get moved up into the air in the first place. And we just realized that we calculated that in the last portion. So we said that we would have some force, which was equal to mass times gravity, and it would go up some height. So the work to get up there is equal to mg times the height. And that's going to be equivalent to the potential energy stored inside of our object. So potential energy, and I'll just use PE, is going to be equal to mass times gravity times height, mgh. So 10 kilogram box sits 5 meters above the ground. How much potential energy does it possess relative to the ground? So PE is going to be equal to the mass, 10 kilograms, times gravity, 9.81 meters per second squared, times the height, 5 meters. And if we calculate that out, we get 490.5 kilogram meter squared per second squared. Yikes. Joules, which in this case was equal to my kilogram meters squared per second squared. Okay. If we're good about our units and we're good about our equations, then ugly units like that we don't need to worry too much about. We know it's going to end up with the right units at the end. And just to compare that, if we looked at the work done in lifting a 10 kilogram box into the air, so if we had our original question, how much work was there, we knew that the work was going to be equal to mass times gravity times height, and once again, so 490.5 joules. So those guys are the same. Can potential energy be caused by any phenomenon other than gravity? Yeah, we kind of consider that potential energy is always gravity due to position or location. But, you know, we could have essentially potential energy, a stored energy in the form of like pressure in a pressure vessel or something like that. We have springs. So we have like lots of spots where we could have stored energy, and we could kind of call it potential energy. Okay, so our other kind of energy is kinetic energy, and kinetic energy, I'm going to give you the equation, which is 1/2 times mass times velocity squared. Only the velocity is squared, it's not everything that's squared. So 1/2 times mass times squared velocity. So let's look at a problem here. What is the kinetic energy in kilojoules of a 3,300 kilogram truck traveling at 70 kilometers per hour? Okay, so my first concern is 70 kilometers per hour. Not in my normal units. Okay, so let's work at the conversion for that. So what we would want is meters per second So kilometers per hour. I'm going to multiply by 1,000 meters per 1 kilometer. And then I'm going to multiply by 1 hour per 3,600 seconds. And if I multiply those through, what I'll have is kilometers will disappear. My hours should disappear, and I'll be left with meters per second. And if I do that calculation, 19.44 meters per second. There is a shortcut to that. You can see I'm multiplying by 1,000 and then dividing by 3,600. So if I just looked at these guys here, really the equivalent to that is just dividing by 3.6. So 70 divided by 3.6 gets me to my 19.44. So that's a bit of a shortcut. A lot of problems in this section will be given to you in kilometers per hour. However, all the calculations need to be in meters per second. If you take your kilometers per hour and divide by 3.6, you will get your answer in meters per second, which can save you a few minutes on your exams. Okay, so kinetic energy, KE, is equal to 1/2 mv squared. Is equal to 1/2 times 3,300 kilograms, good units, times 19.44 meters per second, and that gets squared. And I end up with a value of 623,557.44 joules. Question asked in kilojoules, so I'm just going to go double check. That will mean moving 3 decimal places back, so 623.6 kilojoules would be my answer. Okay, blind flange is being dropped. It's an object that's being dropped down, and just when it hits the ground, it's going to have some velocity of 12.2 meters per second. Just curious what the kinetic energy would be. So kinetic energy would be 1/2 mv squared is equal to 1/2 times 40 kilograms. Velocity in meters per second, so that's good. 12.2 squared, and would give me a kinetic energy of just under 3,000 joules of energy. Okay. So the next level type question would be then comparing this final case with an original case, and I'm curious, how high was it when it dropped? Well, the way to do that is to understand that the kinetic energy that was at the bottom when it impacted was the same amount of energy that we started with. It was just a different form. So in this case, my kinetic energy at the bottom would be equal to the potential energy that it started with. So my 2976.8 joules would be equal to the potential energy, mass times gravity times height. So the height would be equal to 2976.8 joules divided by the mass, 40 kilograms, and divided by gravity, and I could get a height of 7.59 meters. Okay, so all of a sudden, by looking at energy, I have a way to compare different positions. And as long as I can account for all the energy, then I can find out different states for an object at different positions. So different velocities, different heights, different potential energy, different kinetic energies. So what we would consider that would be a conservation of energy. And when we talk about conservation of energy, what really we're saying is that energy can't be created or destroyed. At least we haven't figured that out yet. It can only be converted. Oops. So, for instance, we can switch from, I don't know, potential energy to kinetic energy to heat. You know, maybe we could take that heat and switch it back to kinetic energy. So we have all kinds of different pathways that can exist. Famous experiment that proved this was by James Joule, and what he had was a little tank of water with a little paddle wheel inside, and that had a little rope that was wrapped around, and went to some mass, and as the mass dropped down, it used up some of its potential energy spinning the paddle wheel. And what he was able to measure is that the temperature of the water that was inside rose just a little bit. And so he was able to make a connection between the change of mechanical energy with heat energy inside of the container. I'm going to put a picture. I've seen the actual apparatus that he used. I got a picture of it. I'll put it on Blackboard for you if you're interested. Calculation-wise, from that, we have some questions that might come out. I'm going to skip this first one for a moment, and I'm going to go to the next one here first. So, cannonball is shot into the air with a vertical velocity of 38 meters per second. What is the maximum height of the cannonball? So, if you have a cannonball and it's going to get shot up into the air, and it's going to start with a velocity of 38 meters per second. And maybe I'm curious, how high does it get? Okay, so in order to do this, what I would do is assign some points. So I might call this point number 1 down at the ground, and I may call this point number 2 up high. 1 and 2. And so what I would say is that if I was to talk about conservation of energy, what I would say is that all of the energy at point 1 would have to equal all of the energy at point 2. And I may not know exactly what I've got, so potential energy that exists at 1 plus the kinetic energy at 2 has to equal the potential energy at, oh, sorry, not 2. Kinetic energy at 1 has to equal the potential energy at 2 plus the kinetic energy at 2. Okay. Because this cannonball starts from the ground, he is going to have a potential energy here of 0 only kinetic energy. And by the time he gets to the top of his flight, he's going to start slowing down to the point where he stops. So he stops for a split second, moving up, and then he starts moving down, which means that at the very top of his flight, kinetic energy is 0. So what that means is kinetic energy at 1 has to equal my potential energy at 2. Moving this into an equation form, kinetic energy is 1/2 mv1 squared is equal to mgh at 2. One thing that's interesting in this question is the only thing I gave you was the velocity. I didn't give you any information about the cannonball itself, so you didn't have mass, you didn't have anything else. What's interesting about that is when I look at this equation right now, mass cancels out because I have one on each side of the equation. It turns out that the mass of the cannonball was irrelevant to the answer of this question. So don't get panicked and think that you don't have enough information. Usually in these you don't get a huge amount of information, but you're still able to solve the problem. So 1/2 times 38 squared is going to be equal to 9.81 times my h2. And if I solve that, 73.6 meters is going to be equal to h2. Okay, let's go back to the previous question we just skipped. Make myself a little bit more room. Okay, so I have a mass of 100 kilograms. Whoops. Try that again. I have a mass of 100 kilograms, and he's going to drop down and hit the ground. And I'm curious about a few things. So essentially the opposite of the cannonball question I just did. So I have an object that's starting from the top and dropping down. What is its velocity on impact? Okay, so let's do that portion first. I'm going to assign some points. So I'm going to call this point number 1. I'll call this point number 2, which means that PE1 plus KE1 has to equal PE2 plus KE2. At the top, point number 1, I'm starting from rest, so KE is 0. At the bottom, I don't have any potential energy left, so that is 0. So PE1 is going to be equal to KE2. MGH1 is equal to 1/2 mv squared. That would be V2. Same situations, my masses cancel out. And if I'm going to solve for velocity, it becomes a little more complicated because it is squared. Okay, so I'm going to isolate everything other than the v squared. So 2gh is going to be equal to v squared, and v is going to be equal to the root of 2gh. So the root of 2 times 9.81 times 20 is going to be equal to v, and that is going to be equal to 19.81 meters per second. Okay, if I'm curious about this, how much kinetic and potential energy will the object have at 0, 10, and 20 meters? I may just come over here. So I'm curious at 20 meters, and I'm curious at 10 meters halfway down, and I'm curious at 0 meters, how much kinetic potential and how much kinetic and potential energy will the object have at those points. Okay, so I might make up a little table. So maybe I say potential energy, kinetic energy, I just care about total energy, and I'll put my height, and that's going to be at 20, we'll say at 10, and we'll say at 0, and we're going to make up a little table here. Okay, so as we figured out in our last problem, at the very top, at the 20 meter mark, what we decided is it started from rest, which meant that my kinetic energy was 0. And at the very bottom, I used up all of my potential energy. So as this thing changed, what happened is I started out with potential energy. It then turned into a combination of potential and kinetic, and then will turn into 100% kinetic energy at the bottom. At the very top, if I want to find out how much potential energy there was, so my PE at, call it the 20 meter mark, was equal to mgh. (100 times 9.81 times 20), and that gave me a value of 19620 joules. So green, 19620 joules, and that was equivalent to my total energy, 19620 joules. Because energy is conserved, these guys stay the same throughout. Which means that then my KE here would also be the same, 620 joules. The only thing that I don't know for sure is the breakdown between potential and kinetic energy at the 10 meter mark, and I can figure that out though. PE at 10 is going to be equal to mgh, so 100 times 9.81 times 10 is equal to 9810 joules. So I have 9,810 joules of potential energy, 9810 joules, and if we subtracted 9810 from 19620, we would find that we have an equal balance at that point. Halfway down, half of the energy had converted to kinetic energy. One thing to caution you about is, yes, we have it where 10 meters is halfway between 0 and 20, and yes, we have switched half of our energy as we go through. Just be careful, because if you were to look at the velocity, we start at 0, we ended at 19.81. The velocity here is not 9.6. No. Just be careful, because velocity is squared in there, that you can't make that same assumption on velocity. Everything else drops in half, but be careful with velocity. Memory serves, velocity at the halfway mark is, I don't know what it is, 14 or something like that. So anyway, just be careful on that type of question. All right, that's the end of our work energy component. We'll see you in the next video.